Okay, so this would be a demonstration of a problem found in the second week of a differential equations course. This would require the student to have completed Calculus 1, Calculus 2, possibly Calculus 3. So there would be a knowledge base that we're working with the student. So the objective would be right here to solve a differential equation by applying knowledge of the exactness criterion using partial derivatives, then integration. And what we're looking for here is this. This is the key formula for exactness. M of xy dx plus n of xy dy is equal to 0. So this would be based on some familiarity with this topic just being introduced, and it'd be jumping right into solving one of these equations below. So we have this equation to solve 3x squared plus 4xy dx plus 2x squared plus 2y dy equals 0. So that being said, we want to look for step 1, we want to check for the exactness criterion. So it's not too bad checking for exactness in this situation. So we want to keep in mind, here's our m. So this is going to be our m here. And here is going to be our n right here. So step 1, checking for exactness, we're going to let the following happen. We're going to let m of xy right here equal 3x squared plus 4xy. We're going to let the n of xy equal 2x squared plus 2y rather. And in between, I would be asking the student if they had any questions about the setup, whatnot. If there were no questions, we would just move right ahead. So what we want to do to find this exactness, to check for it, is we want to take the partial derivative right here and right here of each of m of xy and n of xy. But with m of xy, we want to take the partial derivative with respect to y. Okay, let me back this up. And with n of xy, we want to take the derivative with respect to x. So we're going to be taking partial derivatives with respect to y for the first one here, respect to x for the second one, and there. So the partial derivatives aren't that bad. And here's the nice thing about them. When we take the partial derivatives of each, okay, so the student would need to remember that when taking the partial derivative here with respect to y, we keep x as a constant, okay? And in this situation, the derivative of 3x squared with x as a constant would just result in 0. And the derivative of, partial derivative rather, and the partial derivative of 4x y with respect to y would be 4x. Here, take the partial derivative with respect to x, we're just going to get 4x. And in this situation, if we're taking the partial derivative, and the y value becomes a 0. So the nice thing is dm dy, dn dx, we get our exact match, 4x, 4x. So we have our match, and now we're in business, since we have our match, to do the rest of the problem. So we could say for all real numbers x, y, in a multivariable domain, the function, the equation rather, is exact in every rectangular domain here, D, that we have. And that leads us into step 2. And before we would go into step 2, I would always ask the student if they had any questions and pause at this moment. So step 2 would be finding a multivariable function f such that we have the partial derivative with respect to f, with respect to x here, equals 3x squared plus 4xy. And that goes back to our original of xy. And the partial derivative here of the function with respect to y of nxy, 2x squared plus 2y, goes back up here, boom, 2x squared plus 2y, that's right about here. So we want the originals met. Okay, so that being said, okay, and I make sure the student understood, reviewed what partial derivatives were if the student had questions. So what we want to do here is now integrate in step 2. So step 2 requires integration. And luckily the integration isn't anything worse than anything seen in Calc 1. So here, for f of xy, we want to integrate that m that we had. And we're adding phi y to it. So the original m from before was that 3x squared plus 4xy with respect to that differential dx right there. We're not differentiating, we're not taking the integral with respect to the y, it's with the x. And this is coming along for the ride, the phi of y. Okay, and that's just part of the exactness criterion going back to the beginning. We want it in this form. And if the student had any questions as to why we did that, I would answer them, especially if there was anything specific that the student didn't understand from a previous lecture regarding this. So now just integrating this with respect to x, this becomes 3x cubed over 3 plus 4x squared over 2y plus this phi of y stays as is. And we're going to need that later on. We're going to need all of this actually. This reduces to x cubed plus 2x squared y plus phi of y. So this becomes our key. Okay, so this becomes our key right here. We're going to need this for the final family of solutions. X cubed plus 2x squared y plus phi of y. So now what we're going to do for this is going to be part of the final answer. What we're going to do is take the partial derivative here with respect now to y. So we switch it around. We took the partial with integration with respect to x up here. Now we're going and finding the partial derivative with respect to y. So we're taking this. So the partial derivative with respect to y for this, let's see, for df dy rather, we know that df dy is 2x squared plus 2y. So how do we know that it's that? Well, if we go back to the beginning, right here, our n of xy is 2x squared plus 2y. So we're using that again, and I would also, student would be taking notes. We would go back to this as to where this came from and any questions that the student had. So going back to that, take the partial derivative with respect to y, and let's see what we get there. Well, partial derivative with respect to y is going to be 2x squared plus 2y equals 2x squared plus d5y over dy. So you're setting this basically equal to the original we had. And what we need, okay, in this situation, what we need okay, this x cubed basically goes away. This x cubed went away because taking the derivative partially with respect to y, that's our constant. We're left with 2x squared y, taking the derivative of that. Well, y as just derivative of that would be 1 as a partial 2x squared plus this 2y. Now, going back, that's back to that original of what the n was. 2x squared plus 2y equals 2x squared now plus d phi y over dy. So coming down to this component here, what we need to do is we need to integrate this. We need to integrate, and also I would pause to see if the student had any questions at all in this situation. So we need to integrate what this would be. Now we have a match here, 2x squared, 2x squared. Those technically cancel each other out, so we could assume 2y is equal to d phi of y over dy. So to undo this on both sides, what we're going to do is integrate both sides. So if we integrate this, the d dy goes, and we're left with phi of y by itself, and that's going to be equal to the integral of 2y dy. So 2y dy, the integral of that, is 2y squared over 2 plus c naught. That's our constant. This cancels, so we get y squared plus c naught. It's an indefinite integral, so we have to have our arbitrary constant there. So we now have all of the dirty work has been done. Phi of y equals y squared plus c naught. So the nice thing now is, well, first I'd ask the student if the student had any questions regarding this explanation. And then from there, we go on. Hardest part of the problem is over. So now we have c naught is the arbitrary constant. And from that, we could, step 3, write the family of solutions from what we had up further. So we could say f of xy is equal to x squared plus 2x squared y plus y squared plus c naught. All we're doing is combining those keys that we had before. So we had this component here, x cubed plus 2x squared y plus phi of y, and that's just becoming this. X squared plus 2x squared y plus y squared plus c naught, because we know from here phi of y is y squared plus c naught. So we're just substituting. So the nice thing is, here again, we now have a single parameter family of solutions equal to f of xy equals c sub 1. Or we could substitute here, and this is just basic algebra at this point. We have x squared plus 2x squared y plus y squared plus c naught equals c sub 1. We're just substituting f of xy as that to here. And if we combined our constants just by bringing our c naught over to the right, we get c1 minus c naught. And that would be our c. So the final answer we could have here is x cubed plus 2x squared plus y squared equals c. And that would be our solution. So I would continue to ask the student if the student had any questions. And this is a little bit of a challenge for some students to learn the process of this with exact differential, checking for exactness and solving a differential equation, but it's manageable with practice. So I hope I didn't bore you too much with this. I'm in a coffee shop right now, so see, and hope you have a great day.